Have you ever wondered what makes something hot or cold? It's a question that might seem simple at first, but the answer is deeply rooted in the science of particles and energy. It all comes down to the tiny particles that make up everything around us. These particles are in constant motion, and their movement is what we perceive as temperature. Temperature is a measure of how much these particles are moving. When particles move quickly, the temperature is high. When they move slowly, the temperature is low. The faster they jiggle and vibrate, the hotter something is. This is why boiling water feels so hot. It's full of rapidly moving particles. Heat, on the other hand, is the total energy carried by these moving particles. It's the sum of all their kinetic energy. Think of it like this. A swimming pool and a cup of tea can have the same temperature, but the pool contains much more heat because it has far more water molecules all carrying energy. This is why a pool can store more heat energy than a small cup of tea. Understanding temperature is crucial for explaining everything from the weather to the way stars shine. It helps us predict weather patterns and understand the behavior of different materials. It's a fundamental concept that helps us make sense of the universe. By grasping the principles of temperature and heat, we can better appreciate the world around us and the vast cosmos beyond. To measure temperature, we use scales like Celsius, Fahrenheit, and Kelvin. Each scale has its own reference points, which are crucial for different applications. Celsius is common worldwide. It sets the freezing point of water at 0 degrees and the boiling point at 100 degrees. This scale is widely used in most countries for everyday temperature measurements. Fahrenheit is used in the United States. On this scale, water freezes at 32 degrees and boils at 212 degrees. This scale is often preferred for weather forecasts and household thermometers in the US. Scientists often prefer Kelvin. This scale starts at absolute zero, the coldest possible temperature where all particle motion stops. On the Kelvin scale, water freezes at 273.15 degrees and boils at 373.15 degrees. Kelvin is essential for scientific research, especially in fields like physics and astronomy. By using these scales, we can accurately measure and compare temperatures, which is essential for scientific research and everyday life. Understanding these scales helps us navigate the world around us, from predicting the weather to conducting complex scientific experiments. Just how hot can things get? The answer might surprise you. While our everyday experiences are limited to a narrow range of temperatures, from the chill of a winter morning to the warmth of a summer afternoon, the universe offers some mind-boggling extremes that go far beyond our daily lives. The Planck temperature, a staggering 1.42 times 10 to the 32nd degrees Celsius, is considered the theoretical upper limit of temperature. At this unimaginable heat, the laws of physics as we know them cease to function. Beyond this point, our current understanding of physics breaks down, leaving scientists puzzled and intrigued. Here on Earth, scientists at CERN have created extremely hot temperatures in the Large Hadron Collider, pushing the boundaries of what we can achieve. By smashing particles together at near-light speeds, they've achieved temperatures of trillions of degrees, briefly recreating the quark-gluon plasma that existed moments after the Big Bang, giving us a glimpse into the early universe. These extreme temperatures help us study the fundamental building blocks of matter and the forces that govern the universe, providing invaluable insights into the nature of reality itself. Section 4. Cosmic fireballs, the universe's hottest events. Out in the vastness of space, even more extreme temperatures exist. Supernovae, the explosive deaths of massive stars, can reach billions of degrees. These cosmic blasts release immense energy and forge heavy elements that are scattered throughout the universe. Neutron star mergers, collisions between the incredibly dense remnants of collapsed stars, are even hotter. These events create temperatures so high that they challenge our understanding of physics. Scientists believe temperatures during these mergers could reach trillions of degrees, rivaling the early universe. Studying these extreme events allows us to probe the limits of physics and learn about the universe's most energetic phenomena,